Hi there. This video is on finding and classifying critical points. So you might recall from a previous video where I defined a critical point. That's a point, an XY point, where either the derivative is equal to zero or the derivative is undefined. So we'll start off with just an example, and then we'll get into some of the details about how to find critical points and how to classify them. So we're first going to start off just by applying the definition. We need to find out when the derivative is equal to zero or when the derivative is undefined. Well, that requires us finding the derivative. So I'll go ahead and find the derivative of this example D here. So the derivative of this, I'm not going to go through all of the steps. So the derivative, according to our shortcut rules, is 1 minus 2 over x to the 1/3. I wrote the negative exponent in the denominator, so it might be a little easier to see. Okay, so we're going to have the derivative equal to 0, which means we need 1 minus 2 over x to the 1/3 equaling 0, or we need the derivative undefined. Okay, so let's do both of those so we can find the critical points. So we have an equation here on the left-hand side, 1 minus 2 over x to the 1/3 equaling 0. And there are different ways of solving this. So use your particular method. Typically, I think students want to put the x's on one side and the non-x's on the other side. And you can do this in different ways. I'll do maybe a more traditional way by multiplying both sides, adding to both sides and multiplying both sides. We get something like x to the 1/3 equaling 2. And then if you want to solve this for x, you have to get rid of the 1/3 exponent, which means I'm going to raise it to the third exponent because 1/3 times 3 is 1. And that gives just x to the 1 equaling 8. X to the 1 is the same as x. So we get x equals 8 is a critical point. So we also have to look to see when the derivative is undefined. So our derivative, let me use a different color here. Our derivative is 1 minus 2 over x to the 1/3. And we want to see if that's undefined. So undefined means you can't calculate it. Things we can't calculate are division by 0, square roots of negative numbers, logs of negative numbers, or log of 0, tangent of 90 degrees, or pi over 2. There's different things that are undefined. This one here doesn't have logs or trig or square roots, but it does have division. So we can possibly divide by 0 if this bottom part was equal to 0. And it is equal to 0 when x is equal to 0. So we have a divide by 0 when x is equal to 0. So x equaling 0 is another critical point because that's a point we can't calculate. It's a point where it's undefined. 1 minus 2 divided by 0, there's no answer for that. So we have two different critical points. And we can look at the picture and verify that. So we have this x minus 3x to the 2/3. I think I've prepared that function here. X minus 3x to 2/3. And you can see it's kind of this funky little graph. It goes up, hits a peak, and then goes down. And this peak right here, that's called a local maximum. That's the highest the graph is in this particular location. So x equaling 0 is one of our critical points. It's this one over here. And it's going to be a maximum, local maximum. So this one here is a local max. And you might be able to see, if you look carefully, that at this point, or at this location, the graph comes to a point, a cusp. And so you don't really have a derivative there because it's not smooth. It comes to a point. The left side limit is not equal to the right side limit. So the derivative does not exist. So that's the one we found by setting the derivative undefined. We found x equaling 0, and that was our local maximum. Now hold on here. We also found another critical point that was x equaling 8. And so from this picture I have originally, it's not clear that there's another critical point at x equals 8. So let's expand out here and go over. Oh, so here's 8. 8 is right over here. There's 8-ish over here. And that is a type of critical point. And you can see perhaps in this region, the y values here are smaller, or I mean, I guess higher than negative 4, right? The y value here is negative 3.9. The y value here is negative 3.8. This is the lowest, the minimum y value right here when x equals 8 and y equals negative 4. So this is kind of one of the things that I want to emphasize, is that certainly we can use technology to graph all kinds of things and try to find the answers. But computers are just not very good at exploring and sort of getting an idea of possibilities. It can just kind of go through what it hopes to be the right answer. And I don't want you to just sort of hope that you're finding the right answer. I want you to be confident that you know the right answer. So I know that there are two critical points. There's two really important points in this graph. So I don't have to wonder if I need to look at x equals 8. And I don't have to wonder if there's other things that I haven't found. Like, we don't know based on the graph that there's not another critical value somewhere over here on the right, maybe at 100 or something, right? So we just don't know enough by kind of sort of looking around on a graph that technology has done for us. We need to do a little bit more, which is the calculus, right? So calculus says there's two important points. 8 we can see is actually a minimum because it goes down to the bottom here and it goes up on both sides, right? It's a local minimum, not the absolute minimum. There's lower y values, but in this region over here, that's the lowest y value, right? Right there at x equals 8, the lowest y value is negative 4, and everywhere around this region, the graph goes up from there. So that's called a local minimum. So this one here is a local minimum. Okay, so we have for this particular equation, the example D here, we have two critical points. X equals 8 is a local minimum and x equals 0 is a local maximum. So that's the idea of finding and classifying critical points. So I want to also show you how you can classify the critical points. You can find whether it's a maximum or minimum without having to rely on a graph. And that's the simple idea of increasing and decreasing. A local minimum is sort of like a U-shaped graph like this. And for a U-shaped graph with a local minimum down here, you'll have the graph decreasing with a negative slope and then hitting the minimum, and then a graph increasing with a positive slope. So for a local minimum, it's got to be decreasing, hit that critical point, and then increasing. And contrary-wise, for a local maximum, it's got to be going up, which is a positive slope. It's got to hit our critical point, and then it's got to go down, which is a negative. And it even works with cusps, right? And so, even if it's a weird shaped thing, it still goes up, increasing slope, hits that critical point, and then down, negative slope. So we can easily identify positive and negative slopes just by finding the derivative and finding out when it's positive and when it's negative. And so we oftentimes will classify all kinds of stuff just by looking at the derivative and when it's positive, when it's negative. From our investigation here, we know that it can switch positive and negative, it can switch increasing and decreasing at x equals 8 and at x equals 0. So at x equals 8 and x equals 0, it's possible for things to go from increasing to decreasing. It's possible to switch. And so we need to know whether it's increasing or decreasing on the left and right-hand side of each of these critical points, and that will determine whether it's a local min or local max. So how do we know whether it's increasing or decreasing on these various sides? Well, we just plug in some numbers. So I choose a number here to the left, maybe like -1. I could choose -2 or -0.5. It doesn't matter. Anything to the left there. I know it's not going to change except at 0. So it doesn't matter what I choose in this region. It's all going to be the same answer until it hits 0, in which it could possibly change. I'll choose something in the middle, like +1 or +5 or something like that. And I can choose something over here like +9 or something like that. To make things a little easier, because I can't really cube root 9 very well, maybe I'll choose something I can cube root. So 2 cubed is 8, so maybe I'll choose 27 just because it's easier to do the math with 27. All right, so let me just put 1 here and 27. You could choose any number, but if you choose something like 9, you're going to have to use technology to do the math because it won't come out to be very nice numbers. If you choose something like that. You can choose whatever you want. You choose whatever you want. I'm going to choose 27. I get to choose what I want because I got the pen right now. So I find the derivative at each of these points at -1, and I find the derivative at 1 and find the derivative at 27. And now it tells me in that region whether it's increasing or decreasing. Remember, this is the derivative equation. So I plug -1 into that derivative equation. So that would be 1 minus 2 over -1 to the 1/3. -1 to the 1/3 is -1. So this is 1 plus 2, which is greater than 0. So at -1, the derivative is positive. So this is called increasing. And then we would do the same calculation for a number between 0 and 8. The number I chose, for example, is x equals +1. And I get a very similar calculation. 2 over 1 to the 1/3. 1 to the 1/3 is +1. So this is 1 minus 2, which is -1, which is less than 0. So that means the derivative is negative and the graph is decreasing. And then I would choose a number like 9 or any number that's greater than 8, like 27. And that will tell me whether it's increasing and decreasing in this last region. So I said, why not choose 27? Because I can cube it pretty easily. You can choose whatever you want. You can choose whatever you want. Don't be weirded out by my choice. So 27 into this equation over here, I get 1 minus 2 over 27 to the 1/3. Right? I got to put it into the derivative equation because I'm trying to find the derivative, which is positive or negative slope. Okay, so this 27 to the 1/3 is the cube root of 27, which is just 3. So this is 1 minus 2/3. And even if you're not good at fractions, hopefully you know that 1 minus 2/3 is greater than 1, or I mean greater than 0. So this is a positive number. You have a whole pi minus 2/3 of a pi. You get about 1/3 of a pi left over, but it's greater than 0. All we need to know whether it's increasing or decreasing. Greater than 0 means the derivative is positive, which means the graph is increasing. So we have increasing to decreasing. That's this version over here. So increasing to decreasing means that this thing right here is a local max. And then we have decreasing to increasing. So decreasing to increasing, in between decreasing to increasing has to be a local minimum. And hopefully that corresponds to what we saw on the picture. So on the picture, we should see a local max when x equals 0 and a local minimum when x equals 8. Here's x equals 0, and there's a local max. Everything around here is lower. And over here at 8 is where our local min was. Everything right around here is higher. And there are no other local mins or local maxes because we would have found them when we did our derivative equaling 0 and the derivative undefined. So we know that's it for all the special points for this particular example. All right, so the rest of the video is doing some more examples of these. I'm also going to be showing you a third possibility for a critical point that is neither a local min or a local max. And that will be our goal for this video, is sort of to keep finding critical points, practicing our algebra, solving when the derivative is equal to 0 and when the derivative is possibly undefined, and then classifying them as local mins, local max, or this third as for unnamed possibility. I'll name it right now in case you've heard it before. It's called an inflection point. I'll describe what that looks like and how to find it in a moment. All right, let's do this other example on this page. So I have 12x to the 1/3 minus x. What did we just do? We did x. So this is not too similar. This is kind of like this one backwards, but it has a different exponent. This is 2/3 exponent. This is 1/3 exponent. This is kind of a similar kind of problem. So I might expect something like a critical point when equal to 0 and maybe 1 when it's undefined. We're going to find out. We're going to find out. All right, so enough overthinking. Let's just go ahead and do the math. Let's find the derivative and therefore the critical points. All right, so dy dx. Again, I'm not going to go through all the steps of how to find the derivative. It's 12 times 1/3 is 4, x to the negative 2/3 minus 1. And I have to find out when that's equal to 0. And I also have to find out when it's undefined. All right, so that's how we find our critical points. That's supposed to be a -1. I'm not sure that looked like -1. All right, let's do the solving equal to 0 first. Again, lots of different ways of solving this. I don't want to do the same solution technique every time. So I'll do something a little bit different this time. So I move the 1 over, and I'm going to move the 4 over by dividing by 4. And then I'm just going to get rid of this exponent by raising it to the reciprocal, which is -3/2. That way, -2/3 times -3/2, it becomes an exponent of 1. Here I do 1/4 to the -3/2. So -2/3 times -3/2 is 1. So for here, I get x to the 1, which is just x. Here I get 1/4 to the -3/2. That is 1 over 1/4 cubed. And then the divided by 2 is square rooted. You could do this on a calculator, but I'm trying to help people remember some of their sort of basic skills with fractional exponents. So the square root of 1/4 is just 1/2. So this is 1 over 1/2 cubed. 1/2 cubed is 1/8. So it's 1 over 1/8, which is equal to 8. So x equals 8 is one of our critical points. It's what we got when we had the derivative equaling 0. All right, and then we need, when this is undefined, undefined is division by 0, square roots of negative numbers, those sorts of things. With a negative exponent, we do have a possibility of division by 0. If I write this without a negative exponent, it may be easier to see, perhaps. So yes, it is undefined when x is equal to 0, because when x equals 0, we get 4 over 0 to the 2/3 minus 1, which is 4 over 0 minus 1, which is undefined. So we know that x equaling 0 is undefined. We know x equals 0 is another critical point. So we have 2 critical points, and then we can classify them any way we like. Let's go ahead and do the max min thing just to practice that. We have 0, we have 8. We choose some numbers in between. So I'll choose, let's say, -1, +1, and something larger than 8. We can choose 9. It looks like we're getting the same critical points each time. I'm a little worried that I made a mistake. Let me just double check. I'm going to double check off screen so you don't just see me pause for a long time. Well, I double checked it. It looks all right to me. So if I find a mistake, I'll find a mistake later, but did double check and I can't find anything wrong. So we do get 2 critical points, and there again at x equals 8 and x equals 0. So we can do the same kind of thing we did before, try some values. We could try 9 this time if you like, instead of the 27. Whichever, it doesn't really matter. We're just going to do some values here and plug them into our derivative. So we have our derivative equation is up here, a little bit off the top of the screen. Right here is our derivative equation. So we're just going to be plugging in our test points into that derivative equation. So dy dx, and we're going to plug in x values. So I'm going to plug in the x value of -1. I'm going to plug the x value of +1 and +9. So I'm plugging in a test value in each of these 3 regions and find out what it is. So the derivative is 4 x to the negative 2/3 minus 1. And I just have to do some calculations for each of these values, right? And then I'll know increasing, decreasing. So at -1, I get x equaling -1. I get 4 times -1 to the negative 2/3 minus 1, which is, well, -1 to the negative 2/3 is +1. And then you get 4 times +1 minus 1, which is 3. So this is increasing. And then at x equals +1, I get 4 times +1 to the negative 2/3 minus 1. 1 to the positive, or 1 to the negative, +1 to the negative 2/3 is also +1. So this is 4 minus, oh, so it's also 3. So this is also increasing. Bet you didn't expect that, right? Because usually we have increasing and then decreasing, like it switches. Let's see if it does switch for 9. So at 9, we have 4 times 9 to the negative 2/3 minus 1. So I will have to use a calculator to do this because I can't do 9 to the negative 2/3, you know, without using technology. Or I could do a rough approximation, but let's just use technology to save some time. So we get 4 times 9 to the negative 2/3. Oops, I gotta use parentheses. Negative 2/3, and then that was minus 1. So 4 times 9 to the negative 2/3 minus 1 is a negative number, negative 0.755 approximately. And so this right here, 4 times 9 to the negative 2/3 minus 1, that is a negative number. It doesn't really matter if I write down the decimals. I just need to know it's negative, which means it's decreasing. So going back to our little chart here, we know that in this region, it's always increasing. So it's got a positive slope. Over here, it's also increasing. And over here, it's decreasing. So we know the increasing and the decreasing. Increasing is going up, decreasing is going down. What type of critical point switches from increasing to decreasing? It's got to be a local max. So this is good. Right here, it's got to be a local max. Up, down is a max. But what about increasing? Is that a local max? Increasing is going up. Increasing is going up. That's not a maximum because you have going up, and it's not a minimum either. It's this other thing that I was sort of referencing before, hinting at before. It's what they call an inflection point, a point of inflection. So let's see what that looks like on the picture, and I'll help define it in a moment. So this is the previous graph. I'll just turn that off. Let's see where it is. It's right there. Turn it off. And here's the new equation: y equals 12x to the 1/3 minus x. Boom. Okay. So here's the 0 that we found that was kind of a very odd thing where it wasn't a minimum, it wasn't maximum. You can see that the graph is increasing on the left and it's increasing on the right. So it's increasing and increasing again, and definitely not a local max or a local min. Over here at x equals 8 is where you did have a local max. Here it's lower on the left-hand side or increasing on the left-hand side, and then it's decreasing or lower on the right-hand side. So it's increasing, gets to its zenith, its point up here, its maximum, and then it's decreasing right here, right? So that x equals 8 is definitely a local max, and x equals 0 is neither. We call this a point of inflection. So what do you mean by a point of inflection? Well, this has to do with how the graph bows or turns. Right here, the graph is turning up. We call this concave up. And here the graph is turning down, concave down. So when we switch between this sort of upward turning and this downward turning, we call that a point of inflection. And one of the things we're going to be doing is exploring a little bit more about inflection points as we continue our studies in chapter 4. Okay, so we got one local minimum and one other, which I'm trying to explain to you is named an inflection point. Increasing to increasing is inflection, and yes, by the way, decreasing to decreasing is also an inflection point, right? So you can classify them again using the derivative using the slopes. Okay, so that was our second example there with a little twist thrown in there that we had a critical point, which was neither a local min or a local max. All right, so let's go to some definitions just to make sure that me talking doesn't confuse people on what is what. So I wrote down a bunch of definitions here, including the concave up, concave down that I was just describing a moment ago. So lots of vocabulary. Concave up is one of the words they'll be asking you to describe. An interval of a function is called concave up if the derivative goes down, is decreasing. So whatever the derivative was, it gets smaller and smaller. And what that looks like visually is an upward U shape like this. So concave up, some people say like if you had a bowl shape like this, it would hold water, or it makes a U shape like this, that's concave up, right? We know for sure that it's concave up if the second derivative is positive, right? So that's kind of a key idea. We'll show you why that is true later on. Similar definition for concave down. Concave down means the graph is shaped this way, and it's the fact that the derivative gets smaller and smaller throughout that interval. So the definition of concave down is the derivative decreases, but a lot of people kind of know concave down by the shape. It has sort of this N shape like this. Some people say if you try to put water in this, it would just roll off, right? It wouldn't be able to hold water, right? And in terms of the second derivative, we know for sure if the second derivative is negative in the interval, then it's concave down in the interval. So those are some key ideas about concave up and concave down. And as I just mentioned on the previous example, a point where it switches from concave up to concave down, like this, from concave up to concave down, or from concave down to concave up, can't bend my hand that way. It is called an inflection point, right? So inflection points are when it switches from concave up to concave down or vice versa. And we're going to see to search for inflection points, instead of the first derivative, we're going to be using the second derivative. And once again, when the second derivative is equal to 0 or when the second derivative is undefined, those are possible inflection points. So we get critical points when the first derivative is equal to 0 and the second derivative is equal to 0. And we have not definite inflection points, but possible inflection points when the second derivative is equal to 0 and then the second derivative is undefined. It's a little bit like not as definitive. Unfortunately, you do have to remember that first derivative equaling 0, definitely called a critical point. Those critical points could be local max, local min, inflection points. Second derivative equal to 0, second derivative undefined. Those are possible additional inflection points. So not definite, but certainly we're going to use that to search for them. All right, and then a little summary here on this page, just to kind of keep you grounded as to a strategy. Step number 1, we're going to find the critical points and try to classify them as a local max, local min, or inflection point. Then we're going to solve the second derivative equaling 0 and equaling undefined to find any additional inflection points. And also don't forget that there's other things that we have previously found, like intercepts and asymptotes and things like that. So that's our sort of investigating a function checkoff list. Find and classify the critical points, find any additional inflection points, and remember there's all the important features that you found previously, like intercepts and asymptotes and things like that. All right, let's do some more examples, sort of see this in action, and then sort of we'll be, done with our lesson for today. Okay. Okay, so let's zoom in on this next page and see what our next example is over here. Okay, zoom, zoom, zoom. Oops. Apparently not zooming. Sorry about that. Okay. So we're going to take a function and we're going to see if we can find any local max, local min, and inflection points. So that's this one right here with the x cubed thing. All right, so the first thing we're going to do is find our critical points. So step number one is we're going to find critical points. And we do that by finding the derivative. And finding out when it's equal to 0 or when it's undefined. So setting equal to 0 is just an algebra thing. So we got 0 is equal to 3x squared minus 18x minus 21. If you saw the previous video, you might have seen me solve this equation already. So I reuse this equation. I made it factorable, so we didn't have to use the quadratic formula or completing the square or any of those other techniques. 3 doesn't equal 0, so we have to have either x equaling 7, that will make 0, or x equaling -1. So these two right here are critical points. We also need undefined. So we need to find out when 3x squared minus 18x minus 21 is undefined. And the answer is it never is. Hopefully you can use your pre-calculus to justify this. It's a parabola. It doesn't have any skips or holes. You don't divide by 0. So there's no additional critical points. So no more critical points. So we get 2 critical points, x equals 7, x equals -1. All right, let us look at our little number line here. We have a -1, we have 7, and we have 3 regions where we can investigate increasing, decreasing to be able to classify these as local min, local max, or inflection points. So we're just going to test something like we test x equals 0 as a possibility. Maybe we can test something in between here, between -1. Oh, 0 is not to the left of -1. 0 is over here. So if we test 0, we're testing between -1 and 7. Over here to the left of -1 would be like -2. So we got to test -2 over here in this region. 0 is in this region, and then maybe 8 over here in this region, right? So we test some numbers to see whether they're increasing or decreasing. So I have x numbers, -2, 0, and 7. I have my derivative function, which is this x squared thing. And then I'll just make a little table of values, and I'll plug in -2 and see what I get. So I get 3 times +4 minus 18 times -2 is +36 minus 21. So this is 12 plus 36 minus 21, which is greater than 0. So we know that for the region around -2, the slope is greater than 0. So it's increasing. Then for 0, I can plug in 0 here for the derivative, my derivative equation. So I get 3 times 0 squared, which is 0, minus 18 times 0, which is 0, minus 21. So this is -21, which is less than 0. So this is decreasing. And lastly, I plug in +7. I get 3 times, oh no, I plug in 8. Boy, I think I'm getting a little tired here. The 7 is a critical point. If I plugged in 7, I know I would get 0 because that's how I found 7. I found 7 because that was the x value that made the derivative equal to 0. So if I plugged in 7, I would just get 0 and kind of waste my time. I need to plug in a number to the right of 7, which is 8. Maybe this is nice because then it kind of shows you some of the mistakes that we do as we're learning the material. I know I've plugged in the critical point before and realized, oh yeah, that's why I got 0. So maybe you'll remember this and say, oh yeah, I can't plug in a critical point because I already know the answer. I need to plug a number either larger or smaller. So I'll plug in 8, and I get 3 times 8 squared, which is a very large positive number. 8 squared is 64 times 3. And then we get minus 18 times 8 minus 21. And I will have to do a little bit of math here. 64 times 3 is 180 plus 12, 196. 18 times 8 is a 64 and then 124, and then minus 21. So I get $196 minus $124 minus $21. I still have a positive amount of dollars. I haven't run out of dollars yet because the amount I'm subtracting is like 140 or 150 or something off from 196. So I know it's a positive number, which means it is increasing in this last region. So it goes increasing to decreasing. What goes increasing to decreasing? Well, that's called a local max. And what goes decreasing to increasing? That is called a local min. And we only had two possible critical points, x equals 7 and x equals -1. So there's nothing else to investigate. I know for sure there's only two things, there are only two places where the graph switches, and that's at 7 and -1. And I know what those are. So x equaling 7 is a local max. That's classifying that critical point. And x equaling -1. X equals 7 was the local min. So I got that backwards. At least I'm catching my mistakes, hopefully. Local min at 7. Here's the 7. We said local min. X equals 1 was the local max. We do need to find the second derivative to find any possible additional inflection points. So step number 1 was find all the critical points, classify them. I've classified them. I know there's no other critical points. So let's go ahead and find the second derivative and see if we can find any additional inflection points. So here's my first derivative. I'm going to write it over here. dy dx is equal to 3x squared minus 18x minus 21. And I'm going to find the second derivative. That helps me find any additional inflection points. So that's the way we write second derivative. And then we'll just differentiate this thing. And then we're going to set that equal to 0 or make it equal to undefined. And both of these are pretty straightforward to solve. Equaling 0, we have 6x equals 18 or x equals 3. And then when it's undefined, we need 3x squared minus 18x minus 21. Is that undefined? It's never undefined because it's just a parabola. There's no division by 0. There's no square roots. There's no logs. There's nothing like that. It's never undefined. So there's nothing additional over there. But we do have x equals 3. So is x equal 3? Well, it's definitely an important point. It's where the second derivative is equal to 0. Could it be a local minimum? No. All the minimums and maximums were found when we took the first derivative and found the critical points. If x equals 3 was something like a local min or local max, we would have found it already. So what could it possibly be? And the answer is the only thing that it could be, since it can't be a local min or a local max, it's got to be an inflection point. So this may clarify a little bit about why we say find the second derivative equal to 0 or the second derivative undefined to find possible additional inflection points. So we did find a additional point. It was not a local min or a local max. Therefore, it has to be an inflection point, right? So that's our strategy. Of course, you can find other things if you want, but our goal for this video was to talk about finding critical points and trying to classify them as local mins, local maxes, and inflection points. We will do more investigation about inflection points in the next video. All right, well, that's it for today. Hopefully this video you found useful, and hopefully you will reach out if you have any questions or want any help with any of this material. Thanks.